Hello everyone, welcome to COMP3141. This is the lecture for week 5 on effects and state. So normally when you learn a programming language for the first time, you would start dealing with effects and state very early on. Usually the first example program that you use to demonstrate a programming language is Hello World. But with COMP3141 and with Haskell, we haven't done that. And in fact, this is the first lecture where you'll get a chance to write something like Hello World. But we'll do something a bit more interesting than that. So, firstly, I'll go through some definitions and some sort of theoretical background for what we're doing, and try to motivate why Haskell deals with effects and state differently than most other programming languages do. So, firstly, let's define effects. So effects are essentially all of the observable phenomena from the execution of a program. And by the definition of observable, depends on the perspective from which you look. So for example, if you're looking at observable from the perspective of the user, then things like memory effects, where we read and write to memory, are not observable. Right? But if we are looking at it from the perspective of a particular function, then that particular function may be able to observe memory effects, be able to determine if memory effects have occurred. A more obvious example of an observable phenomena would be something like I/O, because we can clearly observe that input and output is being sent in or out from the computer. So that's even human observable. Control flow is another example of an observable phenomena, like if a function throws an exception, that can be observed by another function. And non-termination similarly. And termination as well. So these are all examples of effects. So it's essentially just stuff that the program does to affect the outside world. So external observability is referring to effects that are observable from outside the function, and this is the majority of the effects we deal with. But there's also stuff called internal effects, and these are effects that may be observable from within a function, but are only observable within the function that does the effects. So for example, things like console I/O and network I/O, and termination and non-termination and control flow and so on, all of these things are externally observable by other functions. But if I have a memory effect, if I read or write to memory, then the internality or the externality of that effect depends on which memory address I read or write to. So for example, if I read or write to a global variable, that would definitely be an external effect, because if I write to a global variable, then another part of the program can see that that global variable has been changed. Whereas if I write to a local variable, then the only part of the program that can observe that change is the part of the program that is writing to that local variable, which is that function. So all of those effects, those internal effects, are contained within the function that is doing them. So we have this difference between external and internal effects, and it's important to keep this distinction in mind. And we'll get into some of the sort of caveats with this distinction a bit later. Okay, so a function with no external effects, by which I mean no effects beyond its return value, is called a pure function. And this is what we've been dealing with for the last several weeks. So for example, whenever we wrote anything of the function type in Haskell, a to b, then that was a pure function. We hadn't been dealing with impure functions at all yet. So a pure function is just the mathematical notion of a function. It's, if you remember from discrete maths or even earlier, a function is just a set of pairs, possibly infinite, mapping every element from the domain of the function, the A type, to the codomain, the B type, right? So it says for every element of this input set, I have an output value. So it's inputs to outputs. So this gives us a bunch of useful properties about these functions. The first one is that two invocations with the same arguments result in the same value. This means if I have f of 7 somewhere in my program, and I determine that that value is equal to 10, then if I see f of 7 anywhere else in my program, then I can just replace that with 10. Without worrying about any of the context in which that f of 7 appears, I know just because if a function evaluates to a particular result, it will always evaluate to a particular that same result if it takes in the same parameters. So beyond the return value of the function, there is no observable effect from this function, right? The only thing it does is return a value. This means that there's no implicit ordering associated with these functions. There's no time notion. So you can't say that this happens before that. That's up to Haskell's runtime system to decide, and it doesn't matter to the result of the function when it is executed. So that's how we can get that kind of lazy evaluation that we've seen. So I ask the question then, are Haskell functions pure? So all of these consequences, these three consequences here, these seem to be things that we have been relying on to do our reasoning with Haskell programs for quite some time. But Haskell functions are technically not pure. And the reason is clear if I show you some of our examples of effects. So Haskell functions only access memory from with parameters that they've been passed in. So the memory effects are all internal, so that's okay. They can't do I/O. We haven't seen any functions do I/O yet. You might think you have, but what's been going on is every time we evaluate a function, we just pass the result of that to GHCI, and GHCI might be doing the I/O. But all of the I/O we've been doing has either been in provided functions that I've written for you, or just being done by GHCI. It hasn't actually been part of your function, so you haven't been printing to a console, or you haven't been writing to any files or anything like that. All of your functions that you've been writing so far have just returned results. But these two bottom effects here, non-termination and control flow effects, are possible in Haskell functions. So for example, if we have head of an empty list, we know that that's a partial function and it can result in a crash, right? And I just said it was a crash, but actually it's an exception, which means it's a non-local control flow event. So it's an observable effect from outside that function. Also, non-termination, so infinite loops, it's another type of partiality of the function, right? So if a function loops forever, which is possible in Haskell functions, then that's another example of an effect that appears in Haskell functions. So the Haskell functions aren't completely pure. The memory effects are all internal, so that's pure. They don't have any I/O effects, so that's good. But then they do have these two kinds of effects. But even though they have those kinds of effects, they are more or less kind of simple enough. These effects are benign enough that they can be treated as if they were pure functions. We can just sort of avoid the cases of partial functions where they hit undefined cases and would crash, right? So whenever we did our equational reasoning before, if we had any partial functions, we just make sure never to call those functions with their undefined arguments, right? So we were very careful when we did our reasoning to avoid any of the problems that can come up because of these impurities. But as I said before, this observability depends on your point of view. And if we go below Haskell's level of abstraction to look at the assembly code produced by GHC, or the low-level C implementation of parts of Haskell's runtime system, then very little of Haskell programs are pure. Even something like adding a number in assembly language is adding numbers into registers, which has an effect on global state. And this effect on global state is clearly an external effect. So even something as simple as arithmetic, if you go low enough on the level of abstraction, eventually you'll find that it's not really pure. So purity is sort of an ideal. It's not something that we can actually achieve. But what we can do is get close enough to it, in Haskell, for example, to be able to reason about functions as if they were pure. So that's why we call Haskell a purely functional language. So why do we care about purity of functions? Why do we want our functions to be pure in the first place? What's the big deal here? Why do we care? Why do we want to avoid these effects? Why can't we just have functions that print to the screen, or functions that write to files, or something like that? Pardon me, there seems to be a motorcyclist enjoying himself outside my apartment. So why do we have to do this? Why do we care? Well, if we allow our functions to just do any arbitrary side effects, then one of the major problems this causes is that it introduces requirements on the evaluation order. So, for example, if you have an effect that requires the state, or a function that requires the state to be set up in a particular way, and then somewhere else you have another function that sets up that state, then you need to make sure now that you call the other function before you call the function that has that requirement. So this is not an observable, if you look at the structure of your program, it's not necessarily obvious that this is the case, but we have these requirements now that this has to happen before that. Not only that, but this is an evaluation order problem. So in Haskell, when we've been doing our equational reasoning, we just substitute equals for equals. If I have let x equal some big expensive computation in x plus x, then I can rely on Haskell to evaluate this in a sensible order and just produce the right result. It doesn't matter which order you do it to get the right result, it will just pick one that's relatively efficient. But if you have effects, suddenly the order in which you do things actually changes the results you get. So Haskell is no longer free to, for example, to rearrange all of our computations to be the most efficient. So this requirement on evaluation order drastically limits the expressivity of our reasoning. Also, it makes our type system lie to us. If I have a function int to bool, in Haskell, I know that barring certain exceptions like partial functions, it will take an integer and return a boolean, and that's it. It's not going to send messages over the network, it's not going to print to the screen, it's not going to launch any nuclear missiles, it's just going to take an integer and return a boolean. But if we allow implicit side effects, then these functions can do literally anything, and there's no way we can tell just by looking at the type. So these, and as I mentioned before, these non-local dependencies are really bad for software design. If we have something like this function over here in module A expects the state to be set up by module B in the other side of the program before it's ever executed, but that dependency is not explicit in the structure of the program, then we have this tight coupling between these modules that isn't visible just by looking at the structure statically. It's no good. And if you do my other course, COMP3141, you'll find that this implicit side effects problem causes issues with strong typing. For example, the fact that arrays are mutable in Java or reference types in ML cause the strong type systems of those languages to have bugs in them. So, in general, if we have effectful programs, things that can do things other than return a value, we can't just substitute the value they return for their body, which means that we can't reason equationally anymore. We just have to reason about states changing as we do in many normal non-functional programming languages. So can we program with pure functions? Of course we can. We've been doing it, it shouldn't say for the past 6 weeks. It's 5 weeks right now. So it was a typo. But yeah, we've been doing this for 5 weeks. We've been writing lots of programs that do lots of different things with just pure functions. So if we can get away with it, what we'd like to do is use pure functions as much as possible. This will prevent us from having to deal with all of those problems that come when we introduce effects. So if we have a program that is stateful in some way, that it might manipulate some external state, then we can write that computation in a pure way as a function that takes in a state, S, and returns a new state, also the type S, as well as whatever result it was going to return. So this is what's called a state transformer. So rather than mutate the state, rather than actually update variables and change things, we take in the old state and return a new state with the changes we want to make applied to it. So this is like a pure approximation of what goes on with mutable programming, with imperative programming. So rather than change the state, we return a new copy. Now you might think efficiency is a problem here if we're copying the state at every step we change anything. And it's true that it is more expensive to do this kind of thing, but there are ways to optimize the use of data structures here. If we use tree data structures, then the overhead becomes logarithmic. And then there are further optimizations GHC can do called fusion, which make this even cheaper. So we can get the cost of this quite a bit down, even though it does increase the cost somewhat. So let's do an example of how we would encode a stateful computation using this kind of state parsing technique. So I have a tree here, and it's got no labels on it right now, so it's a tree that contains a branch with an element in it and two subtrees or a leaf, right? So this is a binary tree of some kind, and we're given a tree that is just labeled with units, right? So unit is the type with only one value, and that one value is just called unit as well. And what we want to do is assign to each of these nodes a particular number. And we want that number to start at 1 at the bottom left. So it'll be 1, and then 2, and then 3, and then in the middle 4, and then 5, and then 6, and then 7. So we're actually starting down here, and we work our way up. Now, in C or something like this wouldn't be too hard to do. We'd have a global or static variable, which would be our counter, and then we would proceed recursively down to the left, and every time we find a leaf node, every time we see a node, we just increase our counter and put the old counter value in the place of the unit. And this requires us to be able to increment our counter, to change it, right, to mutate our state. But we don't have that in Haskell, at least not yet. So what I'm going to do, let me open up a terminal. Here we go. And I'll just open up the correct file. Let me find it. Where am I looking? Yes, it was here. We want the state monads. So let's look at tree labeling. We've got here our tree labeling function. I'll make it even bigger than that. There we go. And now I want to assign to a particular tree node a number, right? So this is taking in a tree labeled with units and returning a tree labeled with integers. And I'm going to do this with the help of a helper function that I'll call go, and it will take in my tree as well as a starting number. It will start it off at 1. So if I give the type of go, it's going to be given a tree of units and a current counter, then give me a tree of integers. Now, if I see a leaf, then my current counter C stays the same. Oops. It's not just going to give me a tree of integers, it's also going to give me the next counter along, right? So here my counter stays the same and I return a leaf. And here, if I have a branch with an element in it, a value, a left and a right, and the counter, well, I know this value is a unit, right? That's the only possible value it can be because it's tree of type unit. But my return tree will be tree of type integer. So first I'm going to go on the left subtree with my current counter. And it's going to return to me the next counter that I get, as well as a new version of the left subtree. Remember, instead of updating the state, we produce a new version of the state. Copy new version. And then we will say that the new value that we want to put in is going to be the counter C prime. And the right subtree is going to be C double prime R prime. When I go on the right, this time I start the counter off at C prime plus 1, which is my next value after the counter I just used for V. So here we're keeping track of our counter by having it as an extra parameter to a recursive function, right? This is similar to what you may have done in assignment 1 to keep track of the extra pen states, for example. So we'll have our new version of the left subtree, our new counter value, and our new right subtree. And the overall counter we'll return is C double prime. And then we have a branch, the new counter value, the left subtree, right subtree. And we put it all back together like that. Okay, so let's see if this solves our issue. It's not very pretty looking. In fact, it's quite hard to read, but we'll look at addressing that in a moment. But if I go open up my stack REPL, load state monads, it doesn't find it. Or maybe it's not called that. Oh, it's called tree labeling. My mistake. Doesn't like it because GoT1 returns a tuple of our new state and our tree. So this is actually going to be, we just want the tree. Don't know why there's so much background noise today. But anyway. Okay, now it seems to be working. So if I go label, I'll just do a very boring tree here. Branch, branch, leaf, leaf. So this is just a triangle. But we should expect the left subtree to have 1, the middle to be 2, and the right subtree to be 3. And indeed, that's what we get. Excellent. So our label function works, but it's not as pretty as it could be. So let's look at how we can address that. We're going to use a data type to simplify this. And this data type is built in to Haskell's standard library called the MTL. And this data type is called state. We don't worry too much about how it's implemented just yet. We'll get to that in a moment. First, I just want to show you how it's used and what it is. So it's this thing called state SA, and you can think of a value of this type to be a procedure that, given some state of type S, will manipulate it, will return a new state of type S, as well as a return value A, right? So it's changing some state of type S and returning a value A. And we have these built-in operations for it. So we have get, which is a stateful computation, a stateful procedure, where the state is of type S, that just returns the current state, right? So it returns S as well. And then put takes in a new state and then updates the state that's currently being manipulated to be equal to this value that we just put in. right? So get takes a state out and puts a new state in. And it returns unit because when you put a new state in, you're updating the state. You don't return anything when you do that. And then pure is the function that, given a value a, will give you a stateful computation that doesn't do anything to the state and just returns a, right? So it's just going to be the sort of identity element here. We essentially just leave the state alone and return the value a without doing anything to the state, but this helps us to make the types line up. And then we also have the sort of evaluation function, the function that actually consumes these things. So given a state SA and an initial state to start it off at S, it will run this whole stateful procedure and give you the return value A, right? So that's what eval state does. So then these are the primitive bits that we can use to put together a stateful computation. So then how do we put them together with other stateful computations? How do we join stateful computations together? Well, one of the simplest ways to join two procedures together is to sequentially compose them, do one after the other. And we do this in Haskell by writing this do block. So we say do, and then put a stateful computation or a stateful procedure. So put 42 is an example of a stateful procedure that updates the state to be 42 and then returns true, right? So we say do this and then do that, right? And that's what the do block does. So these are on the same indentation level. And this actually is equivalent to using this function here, which is called the sequential composition function. And it is given a stateful procedure that returns A. It doesn't worry about what the return value is, and a stateful procedure returns B. It will do this first one that returns A and then throw away the A and do the second one that returns B, producing a new stateful computation that returns B, right? So this new stateful computation that is returned is the sequential composition of the two arguments. We also have another sequential composition function that is a bit more powerful, and it lets us do something with this return value of type A, right? So for example, we have, if I have this, look at this type at the bottom here, I have given a stateful computation that returns an A, then given a function that decides what stateful computation to return based on that A, I'll give you an overall stateful computation that returns a B, right? So essentially it's saying do this A and then do this stateful computation that returns an A, and then based on the A, I'll decide what to do next. And then I'll do that stateful computation, and it puts these two things together to give you an overall stateful computation that returns a B. So sequential composition here is actually just the same as bind, except it ignores this A value. There's a very annoying high-pitched whine in the background. There's so much background noise, I'm sorry, it's probably all being picked up in the microphone. Anyway, so let's use some of this notation and put this into practice a little bit by implementing another built-in state function called modify. So I'll just open up another, I can put it in here even. Modify takes in a state, and given a state SA, and gives you a stateful computation that will run this function S to S on this current state. And that's it. And it'll just return unit. So modify takes our function, and we first read the state and then put f of the state, right? So what I did is take the state out. Remember, get, if we go to the types, is of type state S, and then it returns the current state. So I take the current state, I apply f to it, which gives me a new state, and then I put it back into the current state, right, using put. And so that's what modify is. So this is another built-in function, but you can just as easily define it yourself that way, right? But it's built in. Okay. Next, we have now we can use this to simplify our tree parsing code. So I'm going to leave this version here, but I'm going to write another version called label prime. It's got the same type, and label prime will also call a go function, right? And I'll just leave it like that for now, and I'll show you why in a minute. Go will have a different type. It's going to take in our tree and be a stateful computation that manipulates a state of type integer, right? Our state here is an integer, and returns a tree of integers. And then I can write each of my components now. So when we have a leaf, all we want to do is not change the state at all, right? Remember here that the state is not being changed. C is just being returned as C, and return a leaf. And we have our state primitive here, pure, that takes in a value A to return and just doesn't change the state at all and returns that value. So that's what we're going to use here. We'll say pure leaf. And then we need to do a case for branch. And I'm going to need to do a few steps here. So I will say do, and then we have first. The first step we want to do is run ourselves on the left subtree. Go L. And then we'll get back from that a new version of L. And then we want to modify the current state to be increased by 1. But before we do that, our new value for the center of the tree will be the current state, get. And then we increase the state by 1. We could also go, instead of modify here, I could say put v plus 1, right? It's the same thing. And then we go to the right-hand side, like that. And now we've gotten all of our bits and pieces, and now we just need to return. So we say pure, and then we return branch with that value, the left subtree and the right subtree. So now you can see that this stateful computation is modeling the same stateful computation we wrote up here, except instead of passing this integer in as an input and an output to the function, we just hide it behind this state constructor. So if I go eval state here, it takes the stateful computation and an initial state, which we remember is 1, right? We start at 1. So now that should, if I did it correctly, oh, I have this as well. Yep. Okay. So that is that. And now if I go label prime and type in the same tree, it should give me the same result. And indeed it does. So this is quite a bit cleaner way to write the same thing. Cool. So here we got to use quite a few of our operations. Implicitly, by using this do notation, we use the greater than sign and the greater than equal to sign, which is essentially called sequential composition and bind. So we used both of those. We also used get to read the current state, put to assign a new value to the state, pure to return a value without changing the state, and eval state to execute a stateful computation. So very good. That's that. So how is this state type implemented anyway? Well, it's exactly what we did before. So state is internally a function from the current state to a new state plus the return value, right? Which is the pattern that we were doing before to implement our tree labeling. So if we try to implement our state operations using this new type, let's just put it in here. I'll call this state prime because there's already something called state in the standard library. Like that. And now what we want to do is implement each of these built-in operations. So how do we do get? Well, get is of type state SS. I'll be putting primes on all of these to make sure they don't clash. So we have our state computation with the function, and it's just the function that, it's just going to be the function that, given an S, returns that same state as well as, oh wait, I'm looking at the wrong thing. The state here, yep, there we go. So it will read in the current state and then return that state as the return value as well as the new state, right? So it doesn't change the state and it just returns it. We also have put, which is similar. We'll put prime. And we've got our new state. Pardon me, it should be like that. So we have our new state to put in, and the stateful computation that we want is given an input state, which we'll throw away because we're replacing it with our brand new state, return the state we want to put in as well as unit, right, which is our return value. So that's put. Pure is given an S and a state prime S A. Sorry, it should be given an A and give state prime S A. Pure prime, we have our A, and we say we have a stateful computation that given an S returns an S and our value A. So here it's not changing the state, it just returns the state as is, as well as our new value A. Right, so these are the three basic operations, and then eval state is essentially, so we've got state SA, S to A, sorry, this should be state prime. Then eval state takes in our state function, and now we call it with the initial state, and we just get the return value out using second, which is exactly what we were doing before. Right here we called second on our function. So this is actually just showing that our implementation of this function using the state structure is exactly the same actually as this state passing one. It's just a lot neater. Now we still need to implement the bind function. So we have state prime S of A to state prime S of B to state prime S of B. So what this is saying is I have a stateful computation on the left hand side and a function, let's call this S, C, and a function F here that given an A will give me my stateful computation that returns a B. So what I want to do first is write a stateful computation that given an S, right, which is my initial state, the state that I start from, I'm going to call the left-hand side, this one that returns an A, with that state, and it's going to give me a new state and the A, right? And then I want to call F, and then I want to call F with that A value, and I know it's going to give me a state computation, a second one, and then I will call that second computation with the state that I got from the first computation, and it will return to me a new state and the final return value. So this is the bind function. I know it's a little complicated, but take your time with it and let it sink in and it'll make sense eventually. And then we have state prime SA, state prime SB to state prime SB. And this sequential composition function, which is just do this and then do that, well, it's just A and B. Let's just do A, bind, throw away the return value of A, and then do B, right? So this is always what this is. Okay. So these are all our operations, right? And this is just how we implement them. Because these are in the standard library already, I'll add a exclamation mark onto the end so that they're different, but it's the same rough thing. Okay, so these are our stateful operations. So all it's really doing is still just passing in parameters and return values. Good. So that's what's called the state monad, and we'll get to what monads actually are in the next lecture. But for now, it suffices just to understand how we're using them here to simplify our programs. So the next one I want to discuss is when we actually do want to do some effects. So this is a situation where we might want to perform some I/O to actually like communicate with the user or actually do things that have meaningful impact on the world. Or the other reason usually we want effects is if we really need that absolute maximum efficiency by going lower down to the level of hardware. Usually we can get away with internal effects only there, but sometimes you need to use some serious low-level bit mangling to get the maximum efficiency out of your program, and then you have to resort to doing some effects. So Haskell allows you to do effects, but it does so in a very compartmentalized way. So the approach is pure by default. So all of the pure functions that we've been dealing with are still pure, and we keep them separate, and we have this special effectful zone where we compartmentalize all of the effectful parts of the program. So the I/O type, we've seen this state type, and there's another type called I/O. It's just like IOA, right? And that means this is a procedure that when you execute it will return a value of type A, but it might also do some stuff like launch some nuclear missiles or print to the screen, right? So it can have some I/O effects as well. So I/O is not defined like in the Haskell standard library or in the Haskell standard. There's many different ways of thinking of it. You can think of it just as an abstract procedure. You can also think of it as just like a program in another language. Like you could even think this is a C program that returns an A. Inside GHC's implementation, it views it just like the state monad, except the state is really the entire universe, because the input and output could come from anywhere, right? So we could have input and output from the user or from a network or from anything. So really the input to this function is the state of the entire universe, and it can have effects on the entire universe. So therefore its output is also a new universe which it has updated in some way, right? This is an abstract view of it, but this is actually how GHC models I/O functions internally. But there's many different ways of viewing the I/O type, and none of them are wrong, right? But essentially it's just IOA is a procedure that will do some side effects and return an A when you execute it. Now, it's worth noting that this execution, when I execute an I/O action, that's not the same thing as evaluating the function that returns it. So if I look at, say, putstrlen here, which is a function of type string to an I/O action or an I/O procedure, then if I give putstrlen a string, it doesn't print anything. It just returns to me a procedure. That it returns the procedure to print that string. GetChar doesn't read a character. It's a procedure. It's a constant procedure, right? This is a constant. It's not a function. Readline is not a function. There are constants, which are procedures. And we can stitch these procedures together using the same two functions that we used for state. So we can use this bind operator or pure, or we can use that do notation, right? Which is much cleaner and easier to read. So this notation applies for all monads. I/O is one, state is another, and we'll look at several more next week. And we can write essentially what looks like kind of an imperative program, but using these functions under the hood. So it's worth noting, we can convert pure values, just an ordinary Haskell value, to an I/O procedure that returns that value, right, using pure. So given a value, it returns an I/O procedure that returns that same type. However, we can't go the other way. We can't take an I/O procedure and then somehow execute all of its effects and get it to return that value A to us in a pure context. In fact, the only function that gets an A out of the IOA is bind, right? Or like the do notation equivalent, which does take the A out of the IOA and then puts it immediately into an IOB and then returns an IOB, which means that the moment you use any IO procedure inside your functions, then the IO is showing up in the type whether you like it or not, right? So you can never hide an IO constructor from your type system. If we were to allow a function like this question mark, then it would break all of our equational reasoning. For example, suppose I had a random number generator. That's an IO function. It depends on some external state. And then if I evaluated my random number generator and it returned 42, then I couldn't just look at any other place where I did that evaluation and substitute 42, even though that's what the type system would be indicating, because it doesn't say that any effects are happening. So this would allow us to cover up the fact that effects are happening, which we never want to do. So Haskell I/O is infectious. If a function makes use of I/O anywhere, or indirectly, it might call a function that calls a function that does some I/O, then you will see I/O in its type. The type will always inform you if there are effects. Now, technically, there is actually a function that does this IOA to A, but it's called unsafe perform IO, and we have a linter in our course account that will check if you ever use this and mark you down if you do. So just don't ever use unsafe perform IO. It's designed as an escape hatch for low-level hacking and stuff, but don't worry about it for this course. Okay, so ultimately, the only way to actually run an IO procedure is not to evaluate it. That's a different thing entirely. When we do our equational reasoning, no effects are happening. It's when we return an IO procedure, composed IO procedure, and assign it to main, right? Main is the only IO action, IO procedure that gets executed. So the overall architecture of a Haskell program is we have this IO shell, which includes the main function, and then almost all of the logic for that program is in a pure functions inside of that, right? All the programming we've been doing up until this point. And then sometimes we'll have things like that state monad that I showed you earlier, which encapsulates some internal state like that. So we can still encode these kinds of mutable algorithms. So let's do some examples of I/O. I'll just have a drink of water. Okay. So the first example, pretty popular example these days, given an input number n, I want to print a triangle of star characters of the base width n. Okay, let's just, why is it? There we go. Go to our terminal. That's okay. I'll fix that later. I want to load my REPL and load triangles. Oh wait, I'm in the wrong folder. Okay. So we're going to we have a main function here, and it's going to call print triangle with the argument 9. So let's do a base case first. When we get 0, well, we're not going to do anything, right? So we use pure to create ourselves an IO procedure that does nothing, and we return the unit, right? Now print triangle given an n will first print n stars, right? So we want to do, and we're going to do 3 things, right? We're first going to print n stars. We can just do 2 things. Print n stars and then recurse. So first we will print triangle. Oh wait, no. We will put strlen, which is the function that given a string will print it and then put a new line on the end. and it's going to print n stars. So replicate is a function that, given a number, will give you n of that number, n of that element in a list, right? So this will give me n stars. And then I can recurse by going print triangle n minus 1. So there's my triangle. So let's see if it works. Okay, it compiles. I'm not going to actually load it in GHCI. I'm going to show you just that this is actually a program that I can compile and run by going ghc -make triangles.hs. Oops. And now it's compiled triangles, and there's my triangle. Excellent. So that's the first example. Very simple, but it's getting us started. So now let's do the rest of the owl. Let's do a much more complicated example for fun. So this is a game. Now, this game, essentially, we have this n by n maze, right? N is a fixed constant. I'll show you the maze. This is the maze, and we want the player to be able to get from the top left corner to the bottom right corner, right? And we're going to implement this in Haskell. So there's a few bits and pieces here. Now I'll go through this bit by bit, so don't worry, there's a lot of definitions. Firstly, the maze size, our n constant, is essentially fixed. So I just hard-coded it to be 10 because I'm lazy. And we have tiles for our maze, which can be either walls or floors. We have points, which is just an x and a y coordinate. And then this is the first function that we need to implement. So we have some tiles. Our map in our game, just show you the game state here. The game state is, why am I in Korean input? There we go. The game state is a player's location, right, which is a point, and a list of tiles, which is our map. So this means we have a 2D map, but we only have a 1D list of tiles. So the way it works is, if I draw it out in like numbers, say we just had a 4x4 map, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So we would have this layout. So what we can see here is that to get to coordinate like x, y, I need to multiply y by the width of the map and then add on the x coordinate. So the way to do looking up the map at a particular point is take our list of tiles and take the y coordinate times the maze size and add on the x. Sorry about this high-pitched whine, there's nothing I can do about it. It's some construction work going down outside. So we add on our x. Right, so these are our coordinates and we've got our map. So now we want to, I've also written some helper functions here for points. So this will add on a particular amount of x positions, and this will add on a particular amount of y positions to a point. Pretty straightforward. So now what we're going to do is implement our game. And we've got a bunch of pure functions here which handle all of the game logic. So firstly, let's define a data invariant for our game. So I have the game here, I have my player, and I have a map. So the obvious parts of the data invariant is that the player should be within the boundaries of the map, right? So the player's position here, I'll call it px and py. Px should be greater than or equal to 0 and less than maze size, right? And py, similar. Seeing as it's a square map, we use maze size for both. And then how do I say that, well, there's actually an additional condition here. And that is, whatever we have, look up map m at the player's position should be a space, a floor. It should not be a wall, right? It's impossible for the player to walk through walls, right? So this is the extra condition here. Okay, and now if we want to move left, well, the easiest way to do that would be to just use our add x function. And moving left means we decrease x, so we just add a negative number. We'll just say add x minus 1 to p, and then the map stays the same. Now this works, except this allows the player to walk off the boundaries of the map or into a wall. So to fix that, we'll just say let the new state be this, and if our invariant holds for the new state, then return the new state. Otherwise, return the old state, right? This means that I can avoid walking into walls or walking off the boundaries of the map. It will just ignore any moves that are illegal. And move right, exactly the same. We just add 1. And because our map goes top down, moving up is actually a bit more like moving left, because we want to decrease our y coordinate. I know y sometimes goes the other way, but in this case, moving up is decreasing the y coordinate, and moving down is increasing it. And this is the nice thing about having this invariant function. We can use it for all of the checks here. And then for 1, well, we know the game is 1 if the player's position is maze size, maze size. Sorry, maze size minus 1, maze size minus 1. Okay, so there's all our game logic. So now we have a bunch more interesting stuff to do. We have to actually implement the game part. So if you've done any game development before, you know you usually have a game loop which displays the current state, and then based on an event or input or a frame tick, will update the current state and then loop around and display it again. But before we do the game loop, we have to first initialize the starting state. So we have to read in the map that we're going to use, which is read in from this file, which I have here, input.txt. So here's my map. So I want to read this in, and the name of the function to read in a file is readFile. So I'll read in the file input.txt. Now the type of read file is file path, which is just a string, to IO of string. So this will give it a file path, give me an IO procedure that returns a string. So then I'm going to create a new IO procedure, my main function, which takes in that string from the read file and starts the game loop with the game state that consists of the player starting in position 0, 0, and the string is converted into a map. And that's just using a helper function string to map, which I haven't defined yet, right? So now I've started out my game loop. Now there's a few things we have to do here. Firstly, if we won, then we exit the game. The game's over, right? If you win. And we might even print something nice and encouraging. You won, right? And otherwise, we need to display the state, and I've got a helper function to do that. So display, and I'm using a do here to sequence these operations. So display the current state, and then we're going to get a character, right, which is our user input, and then based on what that character is, we'll update the state. So our user could say WASD, right? This is up, left, down, right? We'll also have Q for quit and anything else. Okay, so these are our possible inputs, and depending on what they are, we'll do different things. So if the user presses W, we want to move up, and that will give us our new state. We just call game loop on our new state. And here, this is move down. this is move, sorry, that's not move down, that's move left. This is move down. This is move right. And if we press Q, that means I want to quit the game, so it'll just do nothing, pure unit. And otherwise, if they pressed anything else, it was probably an accident, so we'll just loop around without changing the state at all. Okay, so there's our game loop. So now most of the game is actually implemented. We just need to do the part of the program that reads in a map from a string and the part of the program that prints out the map onto the screen. So reading in the map is not too hard. What we can do is just say, okay, I'm going to do a recursive function because I'm lazy. You can do this with filter and stuff, but this is easy enough. And I'm just going to say, okay, if it's the empty string, return the empty string. If it's a space character, then return a floor followed by a string to map the rest. And if it's a hash character, then return a wall followed by a string to map the rest. And if it's anything else, we just ignore it, right? Including new lines and stuff like that. So this is why the map here could have new lines. It can also have any arbitrary text that isn't a hash, and it will just ignore anything else, right? Oh, wait, no, I can't do that because I put in some spaces. Just got to be careful. Yeah, but I can go any arbitrary text because spaces would muck it all up, but that seems okay. Yeah. Okay, so our parser is very simple. It just loops through the whole string and only looks at spaces and hashes. Now, for displaying the map, this is a little interesting. What we have is a loop that has the current coordinate that we're at and the map passed in, so the list of tiles. And we're actually going to recurse through the list of tiles as we go. So if we hit the empty list of tiles, we're done printing the map, and that means I'm just going to go put car new line, right, to print a new line just to clear everything out afterwards. And otherwise, then we have the current tile of the map is T, and the rest of the map is T's. And the current position coordinate we're at is X, Y. So firstly, we say if X, Y is the player's position, then we want to put the character at, right? Which is the @ sign, which we'll use to represent the character, like in old roguelike games. Then, if the current tile is a floor, or is a wall, let's say, let's print a hash. Otherwise, if T is a floor, then, oh wait, I'm actually going to, do this a little differently. I'll use an if statement. You can use these inside do blocks. So you can say if the character's position is the current position, then we print that character. Otherwise, if T, we can even go case T of floor, put car space, wall, put car hash. And then now after this, I can do more things. Why? Because this is a do block, right? So I do this if, and then I do some more stuff. So what do I want to do after I print this particular character? Well, I want to move on to the next one. But there's two cases here. If X is less than maze size -1, then I just increase X and move on to the next character, no problem. But if I'm at the end of the row, then I want to start a new line and move down in my coordinates. So we'll say if X is equal to maze size -1, then we will do, and we'll say first print a new line, and then when you recursively go to the next tile, your new x position is 0, you go back to the beginning of the line, and your y position has increased by 1. Otherwise, when we loop around, our x position has increased by 1, our y position stays the same, and we move on to the next tile. Okay, so this is our game, now fully implemented, I think, except I will just do a little hack here. We use getChar to read in character input, but that means whenever the user presses a key, it will actually print it on the screen, which I don't like. I think it looks ugly. So I wrote a special version of getChar called getChar Prime, which is down here. Don't need to worry about how it works, but essentially it just prevents the console from printing whatever you type onto the screen. Okay. So now we have here our game. I hope it works the first try. Let's try it. It doesn't like it, of course it doesn't. Let's find out why. So, line 19. Let me see. It looks fine to me, so what's it saying? Oh. I think I just maybe need some parentheses here. Indeed. And add x. Why does it think these must be integers? I'm not sure why it's thinking that, but we'll find out. Oh, right. The minus ones, you can't do that. Oh, I think it's because you can't write +1. I'm a fool. Yes, +1 isn't written +1 in Haskell, it's just 1, because +1 is the function plus applied to the argument 1. I had just had a bit of a brain fart there. There we go. Okay, now let's try the game. All right, we can see our player in the top left corner. I'm going to try and walk around, and if I try and walk into the walls or out of bounds, nothing happens. But my player can dance around the maze, and he can even try to solve it. Whoops, wait, no, not this way. Let's go back. And when I win, I win. So it seems to work perfectly. So there's our game. So there we go. Instead of Hello World, we decided to implement a game. So the cool thing is we got a lot of interesting sort of points to make just by doing this small example. So if I show you the code again, we have our pure core here. All of this is pure, right? And all of this implements the actual game logic that's interesting to us. And this pure code is really the important part. And it's also the part that is easiest to test. We could write an AI that manipulates this game state very easily. We could even have quick check properties that talk about how easy it is to solve the maze or something. All doable because we have this pure logic. We don't need to worry about this imperative stuff, this effectful stuff, to do our testing. So this effectful stuff has been nicely compartmentalized into this outer shell, and inside that shell we have a pure core of all of our actual logic. Okay, so because now we've compartmentalized our effects into this IO type, we've made our type system much more informative. Just by looking at the type, you can tell if a function may have some dependencies on weird effects having taken place or anything like that. And if you see a function int to bool, you know it takes an int and returns a boolean and nothing else, right? Exactly what you want to know from looking at a type like that. So when we have pure code, we don't need to set up or tear down infrastructure in order to run our tests. We don't need state invariants. We don't need anything like that. All of the reasoning we do is just equational reasoning. It's really nice. And type checking gives us very strong guarantees. This breaks down a bit when we have effects. So it's nice to be able to separate the effectful part, which we can't reason about so easily, from the pure part, which we can. So for the rest of this video, I'm just going to show you a few more cool things we can do with Haskell's effect system. So if we want mutability for performance, for example, there's an extra interface on top of I/O called I/O-ref. Now, sometimes students get the two terms I/O-ref and I/O confused. I/O-ref has nothing to do with I/O specifically, except that all of its operations run inside the I/O monad, the I/O type. The I/O-ref type is just a pointer. Essentially, think of it as a pointer. So when you new I/O-ref, it's like malloc. You create space for a value of type A, and it returns to you a pointer to that space, right? And then read I/O-ref takes the value out of the I/O-ref and returns a procedure that gives you that value. Write I/O-ref takes an I/O-ref, a pointer, and an A to put into that pointer, and gives you the procedure that writes to that location the value that you passed in. So these three functions let us do imperative programming, mutating variables, updating variables with Haskell. It's just a bit ugly. So let me show you how that works. So I have a property here, which I'll show you in a moment. We'll get to that later. But first we want to go through a list and we want to do its average. Now the easiest way to do this is to first set up our variables. So we're going to need a running total, which starts out at 0, and we'll call it total actually, and count, which also starts out at 0, but it only increases by 1 each time. And then we have our loop, which I'll write as a function, because we don't really have loops in Haskell, we only have recursive functions. And I want to go through this list, so I'll make it take in the list. If the list is empty, then we don't do anything. If we have an element in our list, then we first read the current total value, and then write into our total value pointer a new value for the total, which is t plus x, a new element x. Similarly, I'm going to read the current count and then write into the current count c plus 1. So the difference between this and what we were doing before with the state monad is the state monad was just hiding parameter passing. This is actually a pointer. It's actually destructively updating memory in place. Okay, so it's a bit more efficient. And now we call our go function here. So what I did here is use a let binding inside a do block. You can do this. You can write let functions like this. You don't write in that case. So you just write let, and then on the next line in the do block, you can just keep going, right? So this way I defined a pure function here, or rather I defined a function that given a list returns a procedure, right? And then I call that procedure, or call that function on the list else, and it will give me the procedure to run after I've set up my total and count. Once I've done that, it should now have updated my total and count variables. So now I will just read my final total and my final count. And now I will return the total divided by the count. And this will be averaging a list using IO refs. So as you can see, this is a much more imperative version of the program. I'm destructively changing these IO ref values. So they're updating at each step. And it's also significantly uglier, but can be significantly faster in some situations. In this case, not so much, but it's a smaller example that I can show you in a few minutes. So now we've averaged a list of numbers using IO refs. And really what we want to do is, if you look at this function that we just defined, it averages the list of numbers, and we know we can define average just by writing a pure function. Just add up all the numbers and divide it by the number of them. But here we've written an impure function that uses IO, and it's kind of awkward because now IO will infect the type of anything that tries to get the average of all the numbers. This is no good. So sometimes when you want to do some mutation for efficiency reasons, but you don't want to infect the types with IO, there's a special type called ST, and it also comes up with its own set of variables. So ST is like IO, except the only thing you can do in ST is manipulate these ST refs, which are like special local reference variables. They're like IO refs, but they only work inside this special ST monet. And this S parameter here is what prevents these variables from leaking outside and having their effects be observable outside the ST computation. Now this ST monad is not accessible in this course. It's just a useful thing to know because if you ever need to do some efficient high performance mutation inside Haskell, you can do it this way. Okay, you can use this ST monad. So it's just worth noting that it exists. Okay, the last thing I want to do today is talk to you a little bit about how we quick check these things. So quick check has its own sort of procedure type. Like property, it has this thing called monadic IO, which given a property MIO, which is its own procedure thing, its own monad, we can assert preconditions, we can make assertions, and we can run IO computations inside our properties. And we can use the do notation that we used for IO and state inside this property MIO thing as well. So it's easiest to demonstrate if I show you an example. So in this example here, we have our average function. And I said, my property is given a list of integers, it will return a property. My property is doing some monadic IO, so doing this IO computations. First, the precondition is that the length of the list is greater than 0, right? So this is like using the arrow operator in normal properties. And then we have take the average by running this IO computation, else, with the list else, and then assert that the average is equal to the sum divided by the length. So this is a property, but it's written in this step-by-step ordering because we can run several IO computations here using the run command and gather up all their results. So I want to show you another example of this. So if I go to my shell for a second, there's this function called this program called gfactor, which gives you the factors of a number. So what I want to do is run this function and test it run this program and test it using quick check. So I have this IO action here, and it will just, given a number, run the process gfactor, or factor on your machine if you're using Linux, and with the number n as its argument. And what we want to do is, inside monadic IO, we want to first run GNU factor with the number n, and we'll get back a string. And then what we want to do is assert that. Now, if we look at the output here, it gives you the number you typed in followed by a colon and then all of the factors. So we want to ignore the first word here. We want to get rid of that one. We only care about these factors. So I'm going to go, first we get the words of the string, and then we drop the first one, right? We get rid of the first number, which is the number we typed in as input. And then I'm going to read all of them to convert them all into integers. And then I will take the product of all of these and assert that it is equal to the number that I put in. Okay, let's see if it works. Oops. Now let's load. Doesn't like it. I forgot to put the word do. I do that a lot. Okay, what else doesn't it like? It expected integer. Ah, yes, this should be integer. IO. Ah, I forgot to call run. So run is the function, if we look at our slides, that takes the IO action to run and gives you a property MIO action to run inside your property, right? So I needed to use run to convert it that way. Now it works. Okay. Let's. Do I have a main function in there? Oh no, I don't. Okay, sorry. Quick check, test GNU factor. Okay, well, looks like the people who implemented GNU factor knew what they were doing. Cool. Okay, so I know this is a short lecture, but I wanted it to be short because these concepts take a while to sink in. And the easiest way to get to grips with them is to practice them. So we did a few examples in this lecture. There's also going to be a good exercise for you to do. And you'll have 2 weeks to do it because of the break. And Curtis will also go through a few more examples in his lecture on Wednesday. Okay, so thank you very much.